Afternoon session. So the first speaker is Alain Lascoux, and he will talk about Gaudin functions of arbitrary levels.
So, thank you. I thank the first organizer, the conference, for inviting me. So there will be no physics in my talk, so I hope that some people can add some physics to it. I'm interested in determinants of the type Isergin-Korepin, but I will generalize them a little, and I will give some applications, for example, to the theory of McDonald polynomials, which already came in several of the talks. So here is my title. Well, my university changed between the name of the university changed between when I applied for the conference and today, because now it's called Paris Est. Well, there are many reasons to it, but Marne-la-Vallée is also Disneyland, so now there is no ambiguity. Paris Est is a university. So now I'm not too familiar with this trick, so it works. So I just summarize the book of McDonald about symmetric function. You see, all formulas for symmetric function can be reduced to three axioms, which are called the axioms of lambda rings. And so the first one is very trivial, is that what are the functions when you have a variable which are of two colors? Of course, you know how to just write the function having a variable having two colors. So here you know how to separate monomials into the blue letter and the red letter. So the second axiom is really Cauchy formula, which can be written as a determinant. And the third axiom is about the platism, which is a composition of symmetric function. But this one is very powerful, but we almost know nothing about it. So it really means that much of the formulas involving symmetric function are related to Cauchy identity. So Cauchy identity is something like that you have a determinant where you have two sets of variables, x and y. And so as is usual in computer science, we have no indices. So we have x we have x belonging to one set of variables. So of course, to write a determinant, you need to order your variable, and you have a second set of the same cardinality. And of course, now this determinant is divisible by the Vandermonde in the x and the Vandermonde in the y, because it vanishes when x1 is equal to x2. It's also, you have the poles which remain when you expand the determinant. So what is left is really the function equal to 1. And so this is one way of writing Cauchy formula. So here, of course, we have to deduce from it a scalar product on symmetric function and an orthonormal basis, which is a show function and so on, but it's just, it comes really from these determinants. And so next case is really when you take a denominator of degree 2. So now you have two ways to polarize a denominator. You can take x minus y, this is what I will take, and multiply by x minus ty, or you can take x minus y plus gamma, so you take a shift. So this was the first case obtained by Gaudin to solve a physical model, but you have this one. This is one which is due to Isergin and Korepin that I want to study and to generalize. So now we have a non-trivial function. Yeah, so I'm not sure to be. So where is the point?
It's a much more efficient way to do it using the
Aha, okay, thank you. Okay, so here, yes, it has shifted up. No, no, it works.
You want to make it work.
Click. So we have an expert. Ah. Can we change the color?
Maybe, but
Okay, so here, what is left once you just take out the evident factor is a function which is symmetrical in the x and symmetrical in the y. And so this is this function that I want to study algebraically. Of course, people want to do other things with Isergin-Korepin determinant. Usually they are not interested in having properties of this polynomial, but let's say it's interesting. In particular, if you know this polynomial, of course you know how to specialize x to 1, x and y to 1, and t to a power of let's say to a root of unity. There is no problem now in taking limits when you know the function. So, but this is not what I want to do. So here, this is what I will study, is that now I have successive powers of t. So Isergin-Korepin determinant was the case for power 1. And I still have the same properties that I have a denominator, which is just a product of all the denominator. I have the two Vandermonde. And what is left is a function which is symmetrical in x and symmetrical in y. And of course, we are computer scientists or combinatorists or physicists, so we run to our computer and we make things like that. That's to say, I try for order 3 with an old version of Maple, as a matter of fact. For order 3, so here I just enter my determinant, and here powers is 2, and ask to expand the determinant, and it's already too big, you see. So, and even if you the computer answers, then the output is fills several screens, so you cannot read the screen. This is a general problem with a function of several variables, and especially a rational function. Then the output cannot be read because your computer doesn't take into account the symmetries or the partial symmetries. And here, before just deleting the two Vandermondes, then we need first to expand the determinant before being able to divide by the two Vandermonde. So here, this method is not really working, but of course, in that case, we have answers, of course. But nevertheless, it's a general problem how to compute with a function of several variables. Professor De Geer has applied for a grant to compute with polynomial in several variables. So we shall see whether it can be accepted. I don't know. Because did you put also some other keywords in your grant application?
are you referring?
Okay, so here. And fortunately, now we have somebody provided a tool. So sorry, could I ask the organizer to go and fetch the portrait of Newton?
I don't touch Felix. I tried this under alarm.
No, but, okay, so everybody knows Newton. I didn't put a picture of Newton, so you see. So Newton divided differences, I will write, well, the definition is here. You first anti-symmetrize, that is, you take a function, you exchange x, zi and zi plus 1. I try to be a physicist, so I use z instead of x. And once you have an alternating function, then you can divide by the Vandermonde in the case of two variables. And this is Newton divided differences. And of course, when the increment, when the variable differ just by epsilon, then it's finite differences. But this has nothing really to do with divided differences, because with divided differences, then you have algebras of operators and which are deformation of the group algebra of the symmetric group, and computation are very different. As a matter of fact, because I have some time, I can explain the theory of Macdonald polynomial in 1 minute. So it works. Okay, so here. So Newton divided differences are operators on polynomial which commute, so they act only on two consecutive variables, the I and the I plus 1. And they commute with a multiplication with symmetric function in the I plus 1, clearly from the definition. So now your space of polynomial in two variables with symmetric function as scalar is a two-dimensional vector space, or module, as the mathematicians say, module. And so here you need to define only what is the image of a basis. So I take a basis which is 1, and the I plus 1. Okay. And the action of the symmetric group, simple transpositions, and which is used, for example, by Young to describe representation of the symmetric group. He was really working on a function of several variables in his first. So for Young, then the image of 1 is 1, and the image of the is the plus 1 is the I. So for Newton, the image of 1 is 0, and the image of the I plus 1 is minus 1.
For Leibniz?
For De Mazure, for De Mazure, we wrote a generalization of Val character formula, and in fact it means that you only write the formula for n equal 2. I give only the type A. Then, and after everything is settled. So here De Mazure is the most trivial one. So because 1 is sent to 1 and the I plus 1 is sent to 0. And so for Macdonald, so 1 is sent to a parameter t. So you have a parameter t. And the I plus 1 is sent to the I. So it's almost the same as Young. In fact, we see in the theory of Macdonald polynomial, if we write matrices, usually you do not write matrices, but you have deformation of really the action of the symmetric group. So now here, these are the operators which allow you to transform polynomials, and really this operator is a one which is used by Macdonald. Macdonald define first symmetric Macdonald polynomials, so which are more complicated. But when you take non-symmetric polynomials, then you have recursion using only pairs of consecutive variables, and the theory becomes much more simple. So these are the different operators which generalize a little the Newton divided differences, but they are of the same type. And in fact, all these families satisfy the Bread relation. So if I call the operator ti, then I have ti plus 1, ti is equal to ti plus 1, ti plus 1. So it's not too difficult to check. And in fact, we can use the same principle, check on a basis. So now this operator only differ in the law for the square. The square of an elementary operation is different according to these different cases. I leave you to write what is the square of all these simple operators. Okay, so here the story. Yes, I will need it, but I will fetch it.
You don't say I can hold it.
Sorry. You know everything about divided differences, so don't ask.
Please.
No, the chairman didn't tell me to answer the question of the.
Well, please answer the question.
What is the image
What
of,
is the question?
if I take the square of for Young, what is the image of Zi? I mean, how can I know the image of Zi?
Yeah, minus.
Because I must have, it commutes with multiplication with symmetric function. So it fixes Zi plus 1 is a symmetric function. So I need to look at the left column where there is the image of a constant. So here I go to the next slide. Okay. And so here, one application of Newton divided differences is to just increase the number of poles. And so perhaps here I can, did you all read this? So here, you see what you do is that if you start with 1 divided by Z1, then if you apply a divided difference D1, then it becomes 1 minus Z1, 1 minus Z2. In fact, the easiest way to do the computation is that you multiply by the missing factor. Now, the denominator is symmetrical, so that you can ignore it. And you have to compute the image of the numerator, which is a polynomial of degree 1, and 1 is sent to 0, and Z2 is sent to minus 1, but minus 1 is plus. So here we have. Okay. And in fact, most of the computation with divided differences reduce to this case, really. So here you see I've increased the number of poles, and I can iterate. I will have as many poles as I need. And so, it's not, I should write better. And so here it allows me in the Isegrin-Korepin determinant to just increase the number of poles by taking intermediate variables, and after I will specialize this variable to powers of t multiplied by y. So here I apply the first operator related to the first row. So I believe I take this because I didn't find the laser pointer. So here I apply the operator operating on this variable, adding a new variable. So I have increased the degree of the denominator in the first row, and after I increase the degree of the numerator in the second row. So finally, now I have a determinant of the types that I wanted with a denominator of degree 2, and I can iterate and have any degree. You see. And of course, this tells you nothing if you don't know how to compute in another manner. So it's a purely formal operation, but we know how to use divided differences. So we make the computation differently to get an identity. So here we have to compute, so we get rid of the denominator, which is a symmetric function. So we increase the denominator to have all the factors. And so now we shall have a computation with just polynomials entries. So now I have to explain the notation, which are perhaps okay, so yeah. You see, I need only one ingredient, one function in the theory of symmetric function involving two sets of variables is the resultant of two polynomials, where when the variables are just the roots of two polynomials. So I need this function, the product of differences this is a fundamental function. And part of 19th century algebras are variation about the resultant. And so here, what I've taken is that I have my variable, please. I have my variable y0, And here I take all the set of the y minus the first variable. So I take product of differences, which was a missing factor. In denominator, I had exactly x minus y0. And so I take now, I've got rid of the denominator by just multiplying by the biggest possible denominator, so that I have only a numerator with this missing factor. And so I have to compute now the image of this determinant applying divided differences, but of course they act in every row like before. And so the outcome, when you know a symmetric function, is not very complicated. Then the outcome is something like that, where you have a Schur function indexed by a rectangular partition plus a part. And now you have a Schur function in a difference of two sets of variables. So one more thing to explain. So here you see the usual. Well, I should save. So usually, when you want to define symmetric function, you first define elementary symmetric function or complete function, which are the sum of all possible monomials. But we need to have really two sets of variables, and even what I write as a difference of two sets of variables. So here is defined this way. You take, so this one is not well. So you take two sets of variables. You take a variable z.
Little bit
Okay. Thank you. So you have two sets of variables, b and a. And the coefficients in the expansion of this function, so you will call the complete function of a minus b. So you use a notation with a the denominator and b in numerator. And so now with this elementary symmetric function, you take all your classical symmetric function once they are expressed in terms of complete function, and you replace your h usually by this new function, okay, involving two sets of variables. And of course, this is compatible with the usual convention, because when b is a subset of a, then the numerator disappears, and what is left are just the sum of all monomials in the difference of the two sets of variables, and so on. So here, okay. And so Schur functions are certain fundamental symmetric functions which are indexed by partition, which for us will be weakly increasing sequences of number. And here what is the difference is that you have a determinant where this one varies. Of course, the variable also vary by rows, and here it varies by column. You have a square matrix where the entries are Schur function in difference of two sets of variables. And so now this is the result that your Gaudin function of level R is a determinant of a Schur function, where you have separated the variable y. In each row you have a new variable y, but the x stay together. Okay, so you have a compact expression, and of course it's better to see one example to be concrete. So here, this is a case for n equals 3, and the usual Korepin-Isergin determinant. So here what you have is a Schur function of index 2, 2, of index 1 to 2 and 2 to 2. And in each row you have the same difference. So here what we have are, we have the variable y1, and the second variable is t multiplied by y1. So I write sets with a plus signs. So it's compatible with the convention of lambda rings. So it's a compact notation for a function. And so how can we use it? But because this function is very near the resultant, then it has a similar property. And so here you see the resultant itself can be written as a Schur function of a difference of two sets of variables. So here this one can be written as a Schur function indexed by a rectangle. So here, so it will be the size of B, and you repeat the size of B alpha times, which is the size of A, and this is. And these determinants really come in many theories, even the theory of orthogonal polynomials or Padé approximant and so on. You have all these determinants. These are Hankel determinants. Well, they have many applications, but for me, these are just a resultant or deformation of resultant. And so here, if these two sets have one letter in common, then you suppress this letter, and now you see these indices become exactly the size of the new sets of variables, so it factors into a product of differences. So which means, so there is really, once you know symmetric functions, there is no computations, everything is immediate. So what you have are functions which specialize in a product of differences of AI minus BG. And so how can we use it? So here we now apply it to our determinant. It exactly means that I have my variable x1 up to xn. If I specialize this variable to just sum of this ti y g, then either the function vanish, let's say either the entry in the determinant vanish or becomes, let's say, becomes, well, sorry, I should say. Here, in fact, the Gaudin determinant will either vanish or become a product of factors of the type yg minus tk yi. So I have a determinant, and the entry either come to 0 or to product of yi minus tk yg, but the determinant itself will have this property. So here, so to, let's say, I go fast of course, but let's say the outcome of the computation is this theorem, that the Gaudin function of level R is the only combination of a Schur function in X, indexed by partitions. So here this is the size of the partitions that you can use, and which have the same specialization when I specialize X to a subset of this set as this function, which is, so I've written this Schur function, but in fact this Schur function specializes in product of xi minus tg yg. So I didn't write, instead of writing plenty of indices, and because we specialize to a subsequence, the statement is that it has the same specialization as this product of Schur function, and each of these Schur functions either specialized to 0 or to a product of yi minus tg yg. Okay. So here it's an explicit, these are explicit specializations, so I have some specialization which are 0, and some specialization which are product of yi minus tg yg, yk, sorry. So with plenty of indices, I eliminated the indices by leaving it like that. So of course, this looks a little formal, but it can be really used in a computation, and I will show you how to explicitly use this theorem. No, before going to this, then I should say that in that case, in the case of the Isargin-Korepin determinant, of course, we can also use the specialization of T to a root of unity. And it's interesting because this is what you need to enumerate alternating sign matrices. So here, in the case of Isargin-Korepin determinant, you have what you obtain is a Schur function indexed by a partition which is of the type 0, 0, 1, 1, 2, 2, 3, 3. Okay, so combinatorists accept dots because you know what comes after. So, okay, so I'll write here. So here, in the case of Isargin-Korepin, the partition which is coming in the picture is 0, 1, 1, 2, 2, 3, 3. So you take just a consecutive number but repeated. And it's true that it was obtained by Professor Okada that if you specialize in Schur functions, then up to easy factors, and it's the number of alternating sign matrices. But we have the same type of property here. That's to say, if I specialize T to root of unity, related to R, of course, then it will give you also the staircase with repeated parts, but now the parts are increasing by R each time, instead of increasing by 1. So here, at least, this function behaves, even if I have no physical model, then it behaves like a physical function, because it behaves nicely at roots of unity. Well, it's a criterion. And so here, for my friend Pasquier, you see, in fact,
Is it normal?
in fact, this Isargin-Korepin determinant can be obtained also as a specialization of McDonald polynomial. McDonald polynomial are polynomial which depend on two parameters q and t.
So this
and
is now for which case when the t is again generic?
Yeah, so here you specialize q to t power 6.
But t is generic, it's not.
Yeah, t is generic. Yeah. And so here, what you get, you really still the parameter t in Isargin-Korepin determinant. And so, in fact, and this you can explain when you really introduce the Hecke algebra. I don't need the affine Hecke algebra, which is a little more complicated, but the Hecke algebra that I already introduced here, which is just the algebra of operators on the ring of polynomial, which send 1 to t and zi plus 1 to zi. These are the only rule of the game that I need. And so here I need operation. So here I need a little different operator that I write square I, because it's a projector. Then I take a polynomial, I multiply now the variables, sorry, I've changed to x. So I multiply by a linear factor in xi plus 1, and after I use a divided difference in xi plus 1. So I recover something of the same degree. And this is a fundamental operation. It appeared in already in this morning. It was called EI. By Pasquier and by De Geer. This is one of the operators, but here it's the realization as an operator on polynomial. Okay, so now what we have a global operator, which is important. This is the thing that I need in the circle, that instead of doing only with two variables, then we do it this type of operation on all the variables at the same time. So we multiply by the t Vandermonde, and we divide by the t Vandermonde, and we now sum over all permutation of the variable. So I could have left the Vandermonde outside the parenthesis. It would give me a sign, and I would divide by the Vandermonde at the end. So this is a symmetrizer which is used, for example, it sends monomials to whole little root polynomial, but it also sends, for example, Macdonald polynomial, non-symmetric Macdonald polynomial to symmetric Macdonald polynomial. So it's really a fundamental symmetrizer. It can be, and this we saw also this morning, that it can be also factored into simple factors, but with Young-Baxter shifts here. So you have to shift the operator. The square I do not satisfy the bread relation, but they satisfy the Young-Baxter relation with the shifts. Okay, so here we need for the formula that I want to describe, we need one affine operation, which is just just a shift of indices in the variable. But of course now I have to say what becomes of xn, and I introduce so an infinite number of variables with this periodicity condition. So xi plus n is equal to xi divided by t. Okay. So now I shall show you that with the Hecke algebra and with this shift, we can obtain the Isergin-Korepin determinant. Okay, so here, I start with a theorem, which is not very pedagogical. So here I take any function of one variable. I take the resultant of all the variable x minus where I erase the first variable. I take a second set of variable y1 up to yn. So here these are product of differences of the x and y, except x1. Now I take this product of shift operators. They are just shift operators. And I symmetrize with the symmetrizers that I've shown you, which is multiplication by the T Vandermonde and alternations. And so what I get is a factor which depends on the functions that you can ignore, and I get the Isergin-Korepin determinant. So the Isergin-Korepin determinant occurs as a symmetrization of a resultant, because in fact, if I can take the case f equal to 1, in which case this vanishes, so this disappears. So here I give a more general theorem, but I don't need this function. So here, in that case, this is what I wrote here. I take the resultant in the x and y, but x1 is missing. I symmetrize, and what I get is the Isergin-Korepin determinant. And let's see how to show it. Well, here I show you the explicit what means this compact formula. So if I expand this product of shifts, then it means that I have this summation. Now, but the variable x1, x2, x3 have been shifted, changed, and so x4 becomes x1 divided by t. And now I shift again, and x4 becomes, so I have x1 divided by t, x2 divided by t, and so on. And in fact, this summation is not very complicated. It's a Lagrange type. Summation. So here I rewrote it, but in fact, more or less, once you decode, it's a really Lagrange interpolation. So perhaps a word about Lagrange. I have nothing with Leibniz, but Lagrange. So sorry, I should prepare more. So what is Lagrange interpolation? So it can be written with divided difference, but here it's written like a summation. So Lagrange is, you have a function, let's say, of n plus 1 variable. x2, xn plus 1. But which is symmetrical in the last variable. And now you take a summation on all, so let's say we can be given also a set of interpolation points of cardinality n plus 1. So what do? Then you write all possible functions that you can write starting with this one. So you pick out one letter in A, and what remains is what I write a minus a, or set minus a. So here you have a function which is symmetrical in the last argument. But to have something like Lagrange, you divide by the product of differences of a and all the variables, all the points which are not a. So this is Lagrange interpolation. And it can be written with divided differences, but of course it's something that you can compute very easily. And so hence the theorem. By the way, I should have mentioned here, this is one application of divided. Sorry, I don't know how to pass to. I have another window. Escape. So here. So I cite my class 6. So here you have these beautiful integral forms, but they are also just a product of divided differences. So yeah, because Lagrange interpolation can also be written as an integral, and this type of thing also can be written just with divided differences. So I go back to and now
View.
At view. So this is modern.
Full screen.
Full screen. Where is it?
In the middle.
Okay. So Control L. You should have told me. Okay, thank you. So here you see divided differences or Lagrange interpolation looks very simple, but in fact many things, once you manipulate rational function, then they can be related really to Newton divided differences. So here I wanted to pay my tribute to one of the organizers.
Which one?
The second one. Okay, so here. Now, in fact, this computation that I've done, in fact, is related to a result obtained by Varna, but which is this time formulated in terms of McDonald polynomial. So here I will still use the notation of lambda rings. That's to say, here what do I have? I take the sum of all complete functions in a difference of two alphabets, but the first one, the letters are just product of two of letters in A and letters in B. So you have compact notation like that. And so what does it mean once you decode? Then you have one set of variable x, one set of variable y. You multiply by 1 minus t divided by 1 minus q. So what does it mean? It means that q1 minus q must be thought as the alphabet of just 1 q, q square, q cube, and so on.
Oh.
Okay. So here what you have now is you have something which are alphabet x, y, 1 minus t, and multiplied by 1 plus q square, and so on. So this compact notation, it's in fact in quotes. You have to put in denominator everything which comes with a plus sign, and in numerator everything which comes with a minus sign, and this is this function. But this function is a generating function of McDonald symmetric polynomial. So it was a definition of McDonald, as a matter of fact, more or less. And for McDonald polynomial, we need another shift than the one that I used before. We need the shift increasing of indices, but now the periodicity, once you increase, then you have to multiply by q. So now we take back our computation. We have the shift here, and we start with this function. But of course, here I just have a symmetric function, but I must only see how the shift act on the alphabet. So here, this is what I do here. You see, I have to see what is the effect of shifting the indices in these sums of alphabets. So here I write it, and this is why lambda rings notation with A plus B and minus C is useful, because what I discover is that if I shift with this operator which includes a Q, then what is the outcome is that I have what I had on the left plus x1 minus xi, x1 multiplied by t minus 1, which means that Q has disappeared from my operation. I've changed my original alphabet, product of alphabets, into just the same plus a difference of two single letters, the letter x1t minus the letter x1. So
Which simply means that x1 is replaced by x1t.
no, it was divided by 1 minus 2. You have to be careful. Yeah. Okay. So, but in any case, so these are very, there is no computation here, just you replace, you apply your definition, and so it means, concretely, what does it mean? It means that your function, once you apply the shift, and when you symmetrize, then something is, well, this is what is left. This commutes, the part which contains Q can be ignored. You are really computing with only the case Q equals 0. Though you were computing with Macdonald polynomial with parameter Q and T, in fact, the outcome of the operation just acting only on the part which involves T, and which is the computation that I already did before, more or less. So here, because it's okay, so it's more or less the resultant that I've written, but I have to change y into 1 above y. So it's just now a reformulation of the preceding computation, which means that apart from changing x into the inverse variable, then I obtain the Gaudin function, but this time now in relation with the generating function of Macdonald polynomial. And so this is the result of Varnar. So here I just, these are rewriting on the same formula, but okay. So here, perhaps it's a little too heavy, so here, Macdonald polynomial, where can be just realized as eigenfunction of some operators that were mentioned in the talk of Pasquier. And so here, this shift operator, in fact, are related to the symmetric function in these operators. And so what the effect of the shift can be on the Macdonald polynomial can be written differently. It's multiplication by these factors. So we have polynomial which are indexed by partition, and the effect of this operation followed by symmetrization is just introducing factors. It's remarkable that if you take the generating function of Macdonald polynomial and you introduce factors, then now the outcome is that you have just introduced a global factor, which is this Issergin-Korepin determinant. So here I'm a little too fast, but let's say it's once, so there is no, it's just rewriting of the same formula, but using lambda rings to make it shorter. So I believe that it's the end of my talk.
We have the time for questions.
Remarque. Remarque.
C'est fondamental. The McDonald, the Issergin Korepin determinant seems to come out everywhere, but just for two, not for the generalization you discussed does not seem to.
So the generalization, it happens that in a paper of Zinjustin, there is something which specializes to the same show function. So perhaps it will come. So you were the referee of my paper, who was complaining about the absence of physical.
Not allowed to ask such questions.
But then to answer your first question, the physics there is that of higher spin version of a XXZ spin chain or fusion of a 6-vertex model.
Okay.
The R, spin R or the 1 plus 1 over 2.
So it was good to call R the level. Because I had to choose a name, but so choose level.
Level is fine.
Problem level?
Well,
What journal it was?
The ones that I saw just
of
Journal of Physics A.
I see.
I tried to. I was invited to a conference in physics, so I thought that I should publish in physics.
So I can ask a question. So you have in this determinant essentially some sequence like 1 t squared t.
Yeah.
So could you replace this by something else like generic?
No. Here I cannot
something.
replace powers of t by generic parameters, so I don't know. But there is a determinant also of the type B, which is the one considered by the G. Then you would have also a factor 1 minus x y, and with successive powers of t. Yeah. So here it's possible, but I don't know with a general parameter. I don't know.
Does this determinant have any interpretation as a character of a GLN kind of representation?
No, not to my knowledge. No. But you see here, I called the morphism, I call the Euler Poincaré characteristic because it first, in fact, it came before McDonald polynomials and so on. It really came in algebraic geometry with the Riemann-Roch theorem. Hirzebruch needed a formula where this parameter could be equal to 1 or minus 1, so he decided to put a parameter to treat both cases simultaneously. So here it's related to flag varieties, which is not surprising because when you have things, the symmetric and linear group have their geometrical counterpart, which is a flag variety for GNN, so it's not surprising.
More questions? Well, let's thank the speaker again.